A photoresistor is just like it sounds. It is a light-sensitive resistor. It's a little cell on the top with little wavy lines like a radiator, and when it gets hit by photons, based on how many photons per second are hitting it, it has a different resistance value. And you can measure the resistance and see how much light there is, which can be used to create things like optocouplers, which is a way to transmit a signal between devices without a physical wire. So you could have an LED on one end and this sensor on the other, and you could use that as a transistor almost, or even to wire up to a transistor, in case you have one circuit that's powered by a very low power, expensive CPU, and the other side is connected to 220 volts with 50 amps running through it, and you don't want any risk whatsoever of the two connecting by any sort of accidental short. And the other thing you can do, of course, is as a sensor. You can detect how much light there is. You can detect how bright a room is. You could use it to make a nightlight that comes on when it's dark, for example. You can use it to detect how much light is in a room to adjust the brightness of a backlight, so somebody can always read the numbers on your display. But let's see how it works. So it's incredibly simple. We just have a photoresistor in the breadboard, and I'm going to put my multimeter across its leads in resistance mode. Resistance mode works by putting across a very small amount of power and measuring it. Basically, you apply a known voltage and then you measure the current. I can't guarantee that's how this is made, but that would be the easiest way to do it. But anyway, right now, if I put this on the 20 kilo ohm setting, it's reading, and it's wildly varying just because of me wiggling around and accidentally shadowing it, about 6.73, 6.5 or so kilo ohms. So about 6,600 ohms. If I move the wires so it's not quite in shadow anymore, because the wire was casting a very small shadow on it, it's more like 5.4. If I put my hand over it, it goes way high. Let's turn this up to the mega ohms. So this is still measuring in units of kilo ohms, but up to 2,000 of them. So right now it's 104 k ohms. If I were to dump out my wires and put this box over it, watch this. It'll go up and up and up, and you can see there's some sort of delayed reaction here. It's finally gone up. It's gone up to more than 2 mega ohms. If I give it a tiny bit of light, just a tiny bit, it's at 600 ohms, 600 kilo ohms, 700. It's charging up. There's a mega ohm. Put the box all the way over and go way high. So basically there's no practical limit. It'll just go up to a crazy number that you would need an industrial multimeter to measure if it's in near total darkness. And that wasn't even total darkness. There's still a slight bit leaking in around these edges. So what about the opposite? Let's shine a light on it. So now, with the light on it, and this flashlight, as you can see, doubles as a self-defense mechanism. It's great for working on electronics because you never know when you'll accidentally make the terminator and you have to defend yourself. But in any case, if I shine a light pretty much directly on it, we go down to only 160 some ohms. What if I set this as low as I can, get it real close right on there, 110, 107 ohms. If I attenuate this as much as I can, get it real close and right on there, I should be able to get it down even further. 96, 97, bright spot of light right there. I got it down to 84 for a second. In my testing, I actually got it down to 60 some ohms. Might just be an attenuation issue. The shape of this beam, there we go. 66, 64, 63 ohms. So it never reaches zero. You're never going to have a short circuit unless you shine, a laser on the thing. In any normal conditions, you're always going to have at least a minimal amount of resistance. But that doesn't matter anyway, because the way that you actually use one of these things is in sequence with another resistor. So I'm going to turn on my power supply. It's not going to show anything interesting. So I'm going to connect from positive power to a 10 k ohm resistor. If I connect through the 10 k ohm resistor straight to negative power, then it's just going through the resistor and wasting power. 5 volts, I have this set on 5 volts. 5 volts, 10,000 ohms is 500 microamps. So even if you use a resistor that's only 10K, you're wasting a maximum of 500 microamps. And you could use a bigger resistor. The bigger the resistor, the slower response time, but that's not a huge deal. So instead of doing that, I'm going to connect from the 10K resistor into the photoresistor and back out of there to the negative. So this is a voltage divider. I have a fixed value resistor and a variable resistor, just like a potentiometer. And the proportion between the two resistors is a voltage divider. We've been over this. So I will measure voltage now over the photoresistor photoresistor. And I will turn the current on my power supply up so it'll start working. And right now we have about 2 volts going over the photoresistor. If I shade it, it goes up. If I shade it really well, we're getting a really high number, pretty close to the full voltage. Remember, the bigger the resistor, V equals I times R. The bigger the resistance, the more voltage is dropped over that resistor. The lower the current, but we're only measuring voltage. We don't care about current as long as there is some current. So the bigger the resistor, the more voltage is over that resistor versus the other one. This one increases its resistance the less light there is. Light causes it to resist less. Basically, light opens it up to conduct. So if I shine the light on it, right now we're getting down to 0.03 volts. So you can immediately see, even with only a 10K ohm resistor, probably even with 100K, you can easily power a transistor with this. So you can use this as a digital switch. A transistor is generally going to need 0.7 or so across its base in order to conduct, and 0.6 is not going to do it. So in the bright light, in the very bright light, this is not going to conduct very much, which means the transistor will not be open. But what about the other way? Instead of measuring the photoresistor, let's measure across the fixed value resistor. So of course it's the opposite, but if I shine a light on the photoresistor, we get nearly the full voltage on the fixed value resistor. And if I shade it, it basically closes the transistor. So you could have it either way. You could have the transistor close in the bright light. You could have the transistor close in the dimness, whichever way you want to do it. But that's simply how you use this. You run a current through it and it changes its resistance based on light. That's it. A light-based potentiometer. I'll cover the uses of a photoresistor in more detail in future videos, implementing an octocoupler and a dimness sensor. So until then, be seeing you.